Hi, I'm Matthew Coleman, and this is my video presentation for the Massachusetts Undergraduate Research Conference. Today I'm going to be presenting the findings of my paper, Potential for Concordance Between Plurality and Instant Runoff Election Algorithms as a Function of Ballot Dispersion. So without further ado, let's get right into it. So first, I want to clear up any ambiguity about what instant runoff voting is, or ranked choice voting as it's more commonly known. So the idea of most voting that you'll see, which is called plurality voting, is that everyone will choose their favorite candidate and whoever gets the most votes wins, regardless of how much that actually is. I could have 10 people, one of the candidates gets 11, the other ones get like 9.9% each, and the 11% will win. Instant runoff voting works a little bit differently. So first, everyone is going to choose the order in which they prefer these candidates, and that's going to be their ballot. For example, in a three-candidate election, instead of just saying, I want to vote for candidate A, you'd say, I prefer candidate A over candidate B over candidate C. Everyone will cast these ballots, and they'll count up the first choice winner, the first choice votes. If someone doesn't get 50% of the first choice votes, then the candidate with the least first choice votes will be removed from the system, and whoever voted for that candidate as their first choice will have their votes counted immediately as a second choice, which would be an instant runoff. And this will continue until one of the candidates receives 50% of the votes, at which point they'll be considered a winner. So this leads to, now that we understand the differences between the two, we might ask, well, how often am I going to get the same result, and how often am I going to get the different result between these two systems? And the answer you'll hear a lot is that instant runoff and ranked choice voting prevent third-party spoiler candidates from splitting the vote and make it so that people aren't afraid to vote for their first choice because they can have their second choice be the other candidate in their party that they like. One of the big examples of this is the 1912 U.S. election, where President Woodrow Wilson's victory was largely credited to the Bull Moose Party from Theodore Roosevelt, breaking Taft's presumed majority. And so this leads us into another question. That's, how can we quantify whether an election is going to have a spoiler or not? Well, a spoiler is probably going to draw away from some large support of another candidate and even out where all the supports are, such that a lower amount that candidate B might have will allow them to win simply because all the candidates have been lessened in their vote counts. So we now have this idea of concentration, that when voters get clumped up less, they're going to start producing different results in a way. So now we need to figure how voters we can measure how voters are grouped up or clumped up, or however you'd like to put it. There are two ways we can think about this. The first is that we might want to consider the size of the concentration, or just how big the clumpiness of our sample is, in which case we're going to use something called the HHI index. Or we might want to see how much uncertainty there is or how much chaos there is in how the ballots are distributed, in which case we'll use Shannon entropy. And you can see on the right, there is Shannon entropy on top and then the HHI index on the bottom. And so we can use these as a sort of like input value of concentration, and then determine how often, given a sort of concentration, our election algorithm will come out the same. And the way that I did this is that I simulated 1 million hypothetical elections using random results. And I sorted these results into very small bins that I could then average out to determine how often at around this concentration of votes we'd have these algorithms produce the same result. And so I have some graphs here of the results. In particular, we see that whenever we have a higher concentration, or usually one or two significant ballot types, we're going to get very large bin numbers, and we're going to have almost 100% concordance. Usually, in order to get these high results, you need to have over 50% in one candidate. So these will just, large bin numbers will just always concord. However, for smaller bin numbers, that means we have very distributed candidates. So these candidates are actually going to have a much higher chance of winning, definitely higher than 0%. In some cases, there's almost a 1 in 4 chance that we'll have one of these candidates, one of the first place candidates, be usurped by a second place candidate. And if we want to just consider what people's first choice candidates are and how often that results in them, given the concentration of first choice votes resulting in a different outcome, we can actually see here that over 60% of the time at high values of concordance, well, high values of discordance, that is, we'll actually see different results between the two systems due to the fact that these voters are now so spread out that we practically have even numbers among all the different candidates for first place support. So it gets pretty close to a coin flip. And we also might ask the question, well, just given how much percent of the first place votes the first place candidate got, how likely are they to win? And we also see that once we're at like approximately a third each, it's a coin flip for 50% on whether the first place wins or not, because it's a matter of where the third place candidate's votes go at that point. And this will steadily increase up to 100% once they get 50% or more. Now, there are a few opportunities for follow-up research here. It would be nice to see how the odds change once we start adding more than 3 candidates, for example, 4, 5, or 6, so we could expand the number of candidates simulated. Or we could increase the accuracy of these bins by tightening the ranges and simulating larger amounts of data so we still got significant results in each range. So this is my presentation, and hope you enjoyed it.